Good morning, everyone. All right, so today we got two topics that we're going to discuss: the characteristics of the Earth and the interior of the Earth. It's an Earth science class, so it makes sense to try and figure out what the overall characteristics of our planet are. All right, so again, I'm going to ask you to copy down some notes. If you can put this in a Google Doc, that would be great. Look over this because it'll help you understand some of the material that we're going to be going over next week, which is plate tectonics. In this case, the modules or the units build on each other. If you really can't understand how the Earth works in terms of processes without understanding the structure of it, that's going to be a crucial comment that I'll make next week. So let's start with a simple question. What's the shape of the Earth? Don't say it's square. We all know better than that. Okay, the Earth, of course, is a sphere. We see plenty of globes. And the Earth bulges out at the equator, and it's sort of compacted down at the poles because the Earth does rotate. We call it an oblate spheroid. The radius of the Earth in kilometers is about 6,000. In miles, if we multiply this number by zero point 0.6, we get 4,000 miles. And let's convert the radius of the Earth in kilometers to centimeters, and I gave you some conversion factors. So this works out, if I take my 6,000 kilometers, multiply it by 1,000 to get it in meters, by 100 to get it in centimeters, it works out to 600 million centimeters, okay, or using the scientific notation that we talked about in the earthquake lecture, it's 6 times 10 to the 8th centimeters. So if we assume the Earth is a perfect sphere, which for all purposes it is, we can calculate its volume using the formula 4/3 pi r cubed, which works out to about 1 times 10 to the 27th cubic centimeters, or 1,000 billion sugar cubes in terms of size. All right, when you're ready, if you need to, you can stop this, but let's go to the next slide. So where is the highest point on the Earth? I think many of you already know this. That's Mount Everest. It's about 5 miles high above sea level. The lowest point on the Earth is the Marianas Trench, about 7 miles down. And these facts are going to be important in the next year. We're going to ask the question, why is it that Mount Everest is so high? Why is the Marianas Trench so deep? And why is it located? Why is Everest located between India and China? Why is the Marianas Trench located on the western part of the Pacific? These are all really good questions. Some of you may already know the answers. We'll find out next week in the Dynamic Earth lessons. So if the mass of the Earth is 6 times 10 to the 27th grams, what is the density going to be? We got to go back to the first week of school. I taught you the rule for density. It's equal to mass divided by volume. So if we take 6 times 10 to the 27th grams and divide it by 1 times 10 to the 27th, you just end up with good old 6. All the zeros cancel each other out because we have 27 zeros in the numerator and the denominator, so all gone. All right, so the next thing I want to talk about is the interior of our planet. And the first thing that I need to say is that we've literally barely scratched the surface of the Earth. The deepest hole that's ever been drilled were by the Russians. It took them 20 years to drill just 7 miles into the Earth. Going into the Earth is really tough. You know, it's one thing to blast off into space. You're just going into empty space. But the Earth is tough. As you get deeper and deeper in the Earth, two things happen. One, the Earth gets hotter, and two, the pressure increases. So even solid steel is going to start acting like a wet macaroni noodle, and it just becomes an engineering problem. How do you rotate that drill bit enough to drill further into the Earth? And the Russians were drilling through solid granite. We do know quite a bit about the interior of a planet, but mostly it's through indirect measurements and calculations, and that's what we're going to talk about next. All right, so one of the things we can do is we just talked about density. We know that rocks on the surface of the Earth have a density of about 3 grams per milliliter that we measured the first week of school. We know that the average density of Earth is about 6. I just calculated that a few minutes ago. So the question is, what do the rocks at the interior of the planet have to be? And think of this sort of like averages on tests. If I told you that half of the class had 50 on a test and the average was 75, what would that tell you about the rest of the class? Well, the rest of the class had to have 100 to balance off the 50, and average is in the middle. And the same way, okay, if we know that the rocks on the surface of the Earth are 3 and the average is 6, the rocks at the center have to be 9 to balance off the densities. So the average is halfway between the 3 and the 6. So then geologists start to ask, well, what kind of rocks and elements do we know of that have a density of 6? And the only ones are metals, things like iron and nickel. So we know at the center of our planet has to have those metals there. By the way, if you're not a fan of all this math, and I know some of you are not, there's another way of doing it. I'm sure all of us at one time or another have been out in nature. We had a compass, and the compass needle pointed to north. Well, why is that? Well, it's because the Earth has a magnetic field. Why does the Earth have a magnetic field? It's because there are metals that are present inside of our planet that generates that field. So there's a couple ways of proving that there have to be metals at the center of our planet. Plus, we have a lot of earthquake evidence. In the 1960s, the United States government built a dense seismic network all around the planet. And I think they did it because they were trying to determine if the Russians were going to set off a nuclear explosion. And certainly you could measure those waves, okay, with a seismograph. But as a result of this network, we've learned a lot about what the inside of the planet is like. All right, so you recall the point where the earthquake originates is called the focus, and we have 3 earthquake waves that are produced there. The P and the L waves travel to all or most of the Earth. But what's been interesting is scientists found out that the point of the Earth opposite to where the earthquake originates gets no S waves. And geologists call this the shadow zone. That's very appropriate. Think of when you cast a shadow. You know, you're out in the sun. Maybe, I hope you're getting outside, getting some exercise while we're shut down as long as you're allowed to. And you notice that you cast a shadow. That's because you're blocking the sun's rays. And the same way, geologists surmise that there must be something at the very center of our planet that was also blocking earthquake waves. And what we figured out is it has to be a liquid. That's the only thing we know of that will stop a shear wave or an S wave from going through. So we know that at least part of the interior of the Earth must be liquid. All right, so now let's go through the parts or the layers of the Earth. We're going to start with the crust. This is the outer part of the Earth. It's the thinnest part of the Earth, about 5 to 20 kilometers thick or miles thick. The continents are thicker than the oceanic crust, and they're made of granite. And the ocean seafloor is thinner, and it's made out of basalt. Remember, we talked about those rocks. They're igneous in the rocks unit about a week ago. Okay, now this is really important. If you can draw this diagram, please do so. If you can email it to me, great, so that I see that you're following along here. But this diagram showing the structure of the Earth is going to be absolutely crucial to the next module of plate tectonics. So let's review what we know about the interior of our planet. First we know is that the outer part of the Earth, the crust, is solid and it's thinner than this line that I've actually drawn here. Then we have the mantle that's composed mostly of olivine. It's solid and it's about 2,000 miles thick. And some of you may wonder how we know this. Okay, we don't have any rocks. We haven't drilled down to the mantle, but we do have volcanoes that bring rocks to the surface. And what we found is that it mostly brings up olivine. In fact, there are some volcanoes that go down to the core that bring up iron as well. Then the next layer is the outer core. It's liquid and it's made mostly of iron and nickel. And then the inner core of the Earth is solid and it's mostly made of iron and nickel. And some of you might be thinking, why is it? Why are these states of matter like they are? Well, the outer part of the Earth, it makes sense. It's solid because the outer part of the Earth is cold and rigid. But as you go deeper and deeper into the planet, okay, it starts to get hotter. And eventually, once you hit the outer core, it's so hot that it melts the rock there and it makes it totally liquid. So why would the inner core be solid? You would think it would be at least be liquid or maybe even a gas, but it's not true. The pressures are so great down there that even though the rock or the metals try and melt, it just doesn't work, okay? The pressure forces them to stay in the solid state. You may notice that there's 2 other regions on the left that I've indicated, and they're going to be important next week. We have the lithosphere, which is the hard, rigid outer part of the Earth, and then there's the asthenosphere, which is soft and almost molten. Think about the Earth like you would an egg. You know, like the egg has a shell to it, which is hard and rigid, and then there's the yolk. And that's what the Earth is very much like. Okay, if you think of that, that sort of egg analogy, it's going to make it a lot easier to try and understand the material that's coming up in the next unit. All right, so some final notes. These aren't too crucial. The moho is the boundary between the crust and the mantle. It was named in honor of some Danish guy whose name is just too difficult to pronounce. And like I said, the asthenosphere is a soft but solid layer. Think of silly putty or Play-Doh. Okay, it's a solid but it's movable. All right, and that's it underneath the hard and rigid hard and rigid lithosphere. Again, remember this model. It's going to be very important in the next unit that we do on plate tectonics. And that's it.